Hello, everyone. In this video, we present a proof of concept demonstration on different development parts to enable AI-driven self-healing operations for energy-efficient dynamic server activation within the 6G Cloud system. Here's what we will cover in this presentation, including a short overview of the demo architecture and development activities, as well as some evaluation numerical outcomes. At a high level, we propose an end-to-end resource allocation loop that integrates CCF, MOF, and AIMLF to manage cloud and edge resources for network services. The loop consists of monitoring, collecting real-time metrics such as CPU utilization that is time-varying based on fluctuating user traffic, AI model training/inference, using historical data to predict future resource usage, anomaly detection, identifying potential SLA violations and network anomalies based on predictions and policy-based thresholds, corrective actions, dynamically adjusting compute resources through self-healing mechanisms. Here is the architecture model overview of the POC scenario. Starting from the bottom of the figure, the physical infrastructure layer includes the UE and IoT devices served by radio units, as well as the edge and cloud servers that host the virtual network functions, VNFs, of a network service. The resources marked in green constitute a resource partition for network service 1, whereas the resource partition for a different NS is shown in red. Moreover, a monitoring agent software component is deployed in each edge/cloud server, collating time series metrics that include the CPU and memory utilization, energy consumption, etc. The CCF layer manages the physical infrastructure through the resource orchestrator component. In addition, the AIMLF blocks for this scenario, ML model, AI, or ML learning module, and performance monitoring component, are overlaid in the autonomic CCF operations, which means that they are directly deployed in the CCF. Finally, at the top, the MOF layer includes the modules responsible for the orchestration of the network service, as well as the SLA policy enforcement. The latter includes identification of server overload to notify the resource orchestrator for further scaling corrections. Going step by step in the scenario story, step 0 is to set any service level threshold associated with the overall energy or CPU consumption through the OSS. Then, the first step is to collect data from the resource partitions through monitoring agents, such as Kepler, Scaphandra, etc. The collected data are stored in the CCF resource database. In the following step, this time series historical dataset is utilized to train offline a machine learning model to provide forecasts of the total CPU utilization of resource partition 1. The following step is to use the trained ML model for inference using real-time sample from the resource database and sending the predictions to the service orchestrator inside MOF. Then, the predictions provided by the ML model are analyzed by MOF's anomaly detector module, which is used to identify resource partitions with potential CPU overload. When a CPU overload is forecasted by the anomaly detector, so triggers an alert to the action taker, which resides in the resource orchestrator of the CCF. The action taker is responsible for performing a corrective action to counterbalance the SLA violation. Among many options, this POC uses a dynamic scaling of the NS resources as corrective action. In specific, the resources are scaled up or down by either activating new servers or deactivating the underutilized ones. Also, performance monitoring tools are responsible for comparing predicted and actual values of the CPU usage and, upon detection of model performance degradation or environmental change, model retraining is initiated by invoking the AI or ML learning component with more recent data. Finally, the updated resource metric reports are continuously gathered in the resource DB and can be used from the AI or ML learning module for periodical retraining. After development and deployment of a Kubernetes-based environment using Prometheus exporters, Grafana, and Kepler tools, we are able to collect several resource metrics like CPU utilization, power consumption, memory usage, all associated with VNFs running on top of the resource partitions. For instance, here you can see the real-time tracking of the power consumption corresponding to an underlying Kubernetes microservice. Using this monitoring agent framework, CCF is capable of collecting live data from running network services for further usage by AIMLF. Model training phase is implemented using a subset of Python tools and MLOps platforms. Using the PyTorch library, we have implemented a long short-term memory network that predicts the upcoming CPU utilization based on history of CPU utilization values. Here you can see the real-time course of the training process, indicating the gradual loss decrease as the number of training steps increases. The trained model is finally storage in the model's database and becomes available for future inference. Upon deploying the trained model in the autonomic CCF operations, real-time samples derived by Kepler are fed in the LSTM model for inference, as you can see here. The model is served using model serving modules, and the inference mechanism is based on PyTorch libraries. Indicatively, the trained model has been trained on the CPU time series data corresponding to real-world traffic traces collected from Torino streets over several months. As we can observe, there are certain CPU usage spikes indicating SLA violation that requires detection and resolution. Periodically in time, performance monitoring tools are used to evaluate the prediction accuracy over a batch of inference samples. This is done by using real and predicted CPU usage values to produce metrics mean absolute error, mean squared error, etc. Here you see the implementation of different anomaly detection methods, including one reactive, which doesn't use ML predictions for activating a new server, a proactive ML-based method with fixed threshold, which uses model inferences to estimate the upcoming anomalies, and a proactive ML-based method with adaptive threshold to ensure lower sensitivity to traffic spikes and allow for more conservative server activations. For instance, here you can see different labeling of traffic time points as normal or anomaly, with the latter being raised when threshold are disrespected and reflecting alarm situation for further corrective actions. After comparing different anomaly detection methods, we can see that after running a batch of steps, the adaptive threshold policy results in the lowest number of active servers, since it dynamically adjusts based on the current traffic pattern, while providing energy savings. The right side figure illustrates the mean power consumption for the three approaches. Evidently, the proactive approach with an adaptive threshold achieves significant power savings as it maintains a lower number of active servers. Note that this is just a demonstration of some indicative anomaly methods, and the developed framework allows also the use of different programmable policies. You can also find the development material in this GitHub link. Thank you very much for your attention.